Okay, today we're going to go over related rates, which is just a way to find the value, the derivative at a certain value when given a separate derivative and a separate value. I should probably explain what the AP test is the AP questions about related rates, what they're going to be about. Usually you're going to be given a value, let's say X, in a separate value or a separate related rate. A separate rate at, let's say, dy dt. Now what you're going to try to do is you're going to try to find the Lincoln equation between x and y. And at that point, you're going to find the derivative of that Lincoln equation and plug in your values. At the time, I struggled with this, but it's really not that complicated. It's quite simple, especially if you remember the mnemonic my teacher taught me, FIGWE. Now, FIGWE stands for find, given, when, equation. So the equation, the f, this is what you're going to try to find. If they give you x and dy dt, which they always will, you're going to want to find dx dt at a certain value. So that's what f stands for, what you're trying to find. Given is what they give you. They usually give you a value of a variable and the derivative of a different variable. And that's what's going to be in your given. When, they'll usually tell you at what point. They may say at x equals 3, or when dy dt equals something else. That's going to be your when you're going to want to solve that variable at. Equation just represents the Lincoln equation. And so this is not necessary. It's just a useful organizer, such that you don't have to go back and read the question all over again. Okay, this is example problem 1. Feel free to do this on your own. If not, that's fine, because I'm going to go over it right now. So first thing we're going to do is draw out a diagram. It's saying that there's a 10-meter ladder laying against a wall. Let's let this blue line represent the ladder. It's going to be 10 meters. Now, of course, this is the y-axis, and this is the x-axis. Now, it's saying that it's sliding to the right at 2 meters per second. And it's also saying that it's asking how fast it's falling when it's 3 meters high on the wall. So when this point is at 3 meters. So now we're going to set up a FIGWE organizer. So what do we want to find? Like, we're trying to find how fast it's falling, and that's going to represent dy dt. Now, given, or g, what does it give us? It gives us the dx dt, which in this situation is 2. Now, when do we want to find it? We want to find it when it's 3 meters off the ground, so when y is equal to 3. Now, the equation, the Lincoln equation, how are we going to relate y to x? This is also a triangle, so this makes it especially easy, but we can say x squared plus y squared equals 10 squared. That's going to be our Lincoln equation. So, like I said earlier, we're going to try to find the derivative of the Lincoln equation. Now, since you're not deriving with respect to x, but rather respect to time, you're going to end up with dx dt. It's just saying, this is essentially the chain rule in a sense, except we must add this whenever we derive a variable. And naturally, the derivative of y squared is 2y dy dt. And this is equal to 0 because any constant when derived is equal to 0. So from here, we can almost fill in our variables, except we don't know what the value of x is. We know that y is equal to 3. We know that dx dt is equal to 2, but we don't know what x is. Luckily, we can find it by using this equation. We can fill in 3 for y, so we know that 100 minus 9, the square root of that, is equal to x. So we know that x is equal to square root of 91. Now, we can fill in the rest of these, so we know that 2 times the square root of 91 times the square root of 2 plus 2 times 3, because y is equal to 3, We don't know what dy dt is because that's what we're trying to find. So we'll just leave that as dy dt equals 0. Now, essentially what we're saying is 4 times the square root of 91 plus 6 times dy dt is equal to 0. So we can isolate dy dt because that's what we're trying to find. And we know that that's equal to the square root of 2/3 square root of 91. And that's our answer. The ladder is falling at 2/3 the square root of 91 when y is equal to 3. Okay, this is example problem 2. I should put a disclaimer up. I did not create this problem. There will be a link to the PDF with the problem that I found earlier. It'll be in the description. So what we're going to do first, well, I'm not going to set up a visual diagram for this. I'm not too great at drawing, but I will put up a Figwheel organizer. So we want to find, essentially what it's asking is we're given a spherical lollipop. The volume's decreasing at 0.08 milliliters per minute. We want to find how fast the radius is decreasing when the radius is 20 millimeters. So what do we want to find? We want to find, like I just said, how fast the radius is decreasing. So that's dr dt, where dr obviously equals, or sorry, where r equals the radius. Now, what are we given? We're given that the volume is decreasing at 0.08 milliliters per minute, where V obviously equals volume. Now, when do we want to find it? When do we want to find dr dt? Well, we want to find it when the Tootsie Pop is 20 millimeters across. Now, this is a bit misleading because you may assume that 20 millimeters, well, that's just the radius. This is actually the diameter. So we're going to try to find it when r is equal to 10 millimeters. Now, what is the Lincoln equation? How can we incorporate both volume and radius into a spherical equation? Well, we can just find the volume of a sphere, which is 4/3 pi r cubed. Now, we're going to derive this. So let's find the derivative of the left side, which is dv dt, because we're deriving it with respect to time. And that is equal to 4 pi r squared dr dt. Because pi in this situation is a constant, and we're deriving with respect to r. So that's why this is this. At this point, we can just substitute in everything. We know that dv dt is 0.08 equals 4 times pi. Now we know that the radius is going to be 10. So that's simply squared. Times dr dt. So this question was pretty simple. We know that dr dt is equal to 0.0002 over pi. Pretty simple.